Good morning. First of all, I would like to thank Professor Roger and Silvia for inspiring us as mathematicians. Thank you very much. This is a great celebration. Also, thank you all the members here. I would like to thank also the organizing and scientific committee for the support. Well, the title of this talk is Coefficient Ideals of the Fiber Cone. This is a joint work. Still, it's a joint work with Professor Perez. Still, it's a paper in process. It's a preprint. I divided this talk into two parts. The first one, we will talk about coefficient ideals. We only will give an introduction, okay, a survey. In the second part, we will introduce you a new kind of coefficient ideals. They are made to give some interesting properties about the fiber cone. So then, let's start with our setup. Here, A, it's just a Noetherian local ring with Crew dimension D greater than 0, and with infinite residue field, okay? And also, the ideal that we are working to, it's an imprimary ideal, okay? Then, here we define the Hilbert. We remind you the Hilbert-Samuel function. This is defined to be a length of that quotient ring. It is known that for any sufficiently large, it is actually a polynomial in N of degree D, exactly the Crew dimension of the base ring. And this polynomial, it's called Hilbert polynomial. To be more precise, it has, eventually, it has this form where you can see many integers. These integers here, they are called Hilbert coefficient of I. The one in the 0 level, it's the most known. It's called multiplicity of I. It is useful, for example, for variety, algebraic variety. For example, we put here some hypersurface, and let's write here. The local ring of V at the origin. And then, for example, the two first one have geometric multiplicity 1. In the second line, we have two hypersurface with multiplicity 2. And in the third line, we have the first one in the third line have multiplicity 3, and the second one multiplicity 4. These numbers, for example, can be seen through these local rings. We can consider the Hilbert function for this ideal M, and then we will have eventually the multiplicity of this maximal ideal. This number for each of these hypersurface, those numbers that I told you are exactly these numbers. They coincide. Okay? Well, a very important ideal that contains I, it's the integral closure of I. If you see the definition of it, its definition, it's very similar to the one that we find in extension of rings, except because here we impose that the coefficient belongs to powers of the ideal I. Okay? Just for the first part, we are assuming that A, it's a formally ecdimensional ring. In other words, it is an unmixed ring. A classical result from this, it says that if you have two ideals, I belonging to J, M primary ideals, so we ask when they have the same multiplicity. It happens when J belongs to I bar. In other words, it is equivalent to having that I as a reduction of J. Okay? So, in particular, this I bar is one that agrees with I in the zero level. Okay? Since this is actually an equivalence, I bar is the unique largest ideal containing I which satisfies this property. Okay? Just to be organized, let's put here these two ideals, I and I bar, and here its property so not only I bar satisfies this, but it has an uniqueness and maximality property about it. Okay? Let's continue. Another ideal called Ratliff-Rush closure of I, it's defined by an union of column ideals. And this ideal have the following property. When I, it's a regular ideal, that is, it contains a regular element, then it agrees with I in all the levels. So it has the same Hilbert coefficient as I, from 0 to D. Okay? And more, it is the unique larger ideal that satisfies this property. Very similar to the first one, the integral closure. Okay? So let's put, actually, here's here. Let's put its property. Here, at all levels. It's important to see how this came up, this property. Actually, Ratliff and Rush, they proved that I tilde and I agrees in powers for any sufficient large. Because of this, these two one have the same Hilbert polynomial. And then they will agree at all levels in the Hilbert coefficient. Okay? Also, the second inclusion here follows because I is a reduction of I tilde. And then you can use the his theorem to prove this second inclusion. Okay, then motivated by these two property, okay, Kirchhoff in the article Coefficient Ideals proved the following result. he actually proved the existence of a unique largest ideal Ik, which agrees with I in all levels from 0 to k. Moreover, this is actually a chain. These ideals were called coefficient ideals. Okay? Actually, if I is a regular ideal, then we have this equality here, because they both have the same uniqueness and maximality property. Okay? So this one here, it's our ID. Another way to write the same theorem, it's using the length. We can use this exact sequence here. And then you use the additivity of the length here to get this equality, to decrease the degree of this length. Well, the result is very abstract. We don't know. In order to obtain new properties, some applications, we need to see its face, something more appropriate. Then Shah proved the first structure theorem. He proved that Ik, it's actually an union, a very weird union. If you see it ranges over minimal reductions of powers of I. If we forget coefficient ideals and just think about this union, it's not obvious to prove that this is actually an ideal. Okay? We know that this is an ideal because of this equality. Being better, he proved a finer structure. He proved that it's possible to find a minimal reduction, only one, so that we have this equality here. See that he only picks from the minimal reduction, only picks k elements. Okay, exactly the level k of the coefficient ideals. So actually, these coefficient ideals are column ideals. Okay. An application, one application for these coefficient ideals, just to emphasize that although you have this equality here, to compute these ideals, it's not easy. It's not easy to find exactly this minimal reduction. Okay. But still, he proved only the existence. In application, we can use this ideal to get an interesting property about the associated graded ring, this blow-up algebra, very important blow-up algebra. Shah proved that actually these ideals control the heights of the associated primes of G. Notice that when k equals 1, this is actually the Serre's condition S1 for G. So, motivated by this result, we ask if it's possible to find a similar result for another blow-up algebra called fiber cone. Then we start the second part. which we only introduce you our results, okay? Well, our setup here, we are assuming that A, it's only an Ethereum local ring of crew dimension D, greater than 0, and such that with infinite residual field. The ideal here, it's only an arbitrary, it's an arbitrary ideal, not necessarily an M-primary ideal. Just to remind you, this is the fiber cone, a graded ring, and its crew dimension, it's a very important number. It's called analytic spread of I. In general, this number, it's between the height of I and the crew dimension of the base ring. Okay? But when I, it's an M-primary ideal, then we have two equalities. They both coincide. So our first theorem of existence, we proved that there exist unique largest ideals between Mi and I, such that the degree of this length, because it becomes eventually a polynomial, is less than S minus K plus 1. Let's just talk a little bit about this. Here we have the fiber cone, and then a very known result for in dimension theory. If we take the length of this is a polynomial in N of degree S minus 1 for any large. Okay? So, see that the degree of this polynomial is actually S minus 1. That is, the dimension of the graded ring minus 1. What this theorem of existence, it proves the following. We find, in other words, submodules of these ones such that the length here is also a polynomial in N, but the degree it will be less than S minus 1 depending on the K. Actually, this is bounded by S minus K plus 1. Okay? Moreover, we get, this is actually a chain between Mi and I. Notice that here, the chain, the first one, the chain, it's IS. here we are working with S, not with G anymore, because the ideal in our case it's arbitrary. Okay? We call these ideals of coefficient ideals of the fiber cone. Okay. Then this is an abstract result for these ideals. We need something more concrete, and then we proved a structure theorem. If you see, it's very similar to the one that we found in Shah's case. But here, in this union, two things are different. The first one, the intersection here. We needed to do this intersection because we needed something between mi and I. It has to be inside of I. Another thing, we put the maximal ideal M here. And the minimal reduction now it's generated by S elements because the ideal, again, it's an arbitrary ideal. Okay? We are not working anymore with D. Also, we could got this final structure. In the same way that Shah did, we found only one minimal reduction, such that we have this equality. And this equality, notice that it happens from 1 to S. And then you used this final structure to get some consequence, some applications. Okay? Like I said, it's not easy to compute these ideals. So at least if we could at least find one of them, it will be good. And then this new Ratliff closure ideal of I, it was introduced by Jaitan and Verma in the article Fiber Cones of Ideals with Almost Minimal Multiplicity. If we see, it's a very similar to the usual Ratliff ideal, except because here we put an M. Okay? And then we used this ideal to prove that the first one in the chain, let's write here our chain. We have to make this intersection because we want something between mi and I, and we are not. We cannot be sure that this, in general, this ideal does not belong to I. We got this. This intersection, it's easier to compute and to use a computer program for that. Also. Then some applications. The first one, we also can use these ideals to control the associated primes of the fiber cone. But as you can see, we only got one direction. Okay? When k equals 1, that condition is actually the Serre's condition S1 for the fiber cone. Okay? Then, let's see. There is this result proved by Hub and Hunek in the article Fiber Cones and the Integral Closure of Ideals. He proved that. See that their hypothesis on A, for example, are stronger. For example, he supposed they suppose that A it's normal and also a domain. Also, they suppose that I it's an imprimary normal ideal. Okay. Another hypothesis is that the fiber cone it's an eight-dimensional ring. So he gives under these assumptions, he gives a necessary condition for the series condition S1 for the fiber cone, okay, through the integral closure of ideals. But then we got a better equivalence. Here we used, if we see the hypothesis here that we have proved, the base ring, it's only an Noetherian local ring. And the ideal, it's arbitrary, with analytic spread greater than 0. In the same way, we assume that the fiber cone, it's eight-dimensional. Then, instead of one direction, we gave an equivalence, a necessary and sufficient condition for the S1 of the fiber cone. Okay? Like I said, it's not easy to compute these ideals, but still, for example, this result, we can get some interesting properties. For example, we can find an eight-dimensional fiber cone that does not satisfy the series condition S1. Let's see just some steps. Sorry. Here, A, it's a formal series ring, module an ideal J. And I and M have this, they are generated by these three elements. Here's the maximal from A. Then after some computation, we found an isomorphism here for the fiber cone, and then we find out that the only minimal prime of the fiber cone, it's actually via this isomorphism, it's only this ideal generated by U and V. It happens because if we have a prime ideal containing this one, then it contains this two one. So, because it has only one minimal prime, we find out that the fiber cone, it's an eight-dimensional ring. On the other hand, now we are going to use to apply that result, that equivalence, our equivalence. We found the two first equalities, but then in the third one, see that we are increasing the powers. In the third one, it's not equal. Then we conclude that actually Mi cannot be the first coefficient ideal in the chain. But see that this one belongs to this one. Then we can use, coming back in a little bit, this equality doesn't happen for n equals 1, then we conclude that this fiber cone does not satisfy the series conditional S1. Another application for that is the following. In this article, on the Cohen-Macauliness of the fiber cone of an ideal, another article from Shah, he suggested the following conjecture. If the fiber cone of the ideal I is Cohen-Macaulay, then the fiber cone of all of the powers of the ideal I also are Cohen-Macaulay rings. Okay? Being honest, I don't know if this result was already proved. Okay? Just I know that in this article, please, if you know, let me know. Okay? But then this result, we obtain something like that, similar in the same way, very similar. We prove that if we assume that the fiber cone is exact-dimensional and satisfies S1 property, then the fiber cone of all the powers of I also satisfies the S1 property. This is easy to prove because of this. We are assuming that if I satisfies S1 and also exact-dimensional, so we can use our equivalence to obtain this. This happens for all of the n, all of the powers. So, in particular, also, we can write in this way. Okay? It happens for all n. But we can use a Veronesian, the Veronesian embedding. This one, by hypothesis, is exact-dimensional. Since this is an extension ring, then this is also exact-dimensional. Then you can use these two, this fact, along with this one, and use our equivalence to prove that all of that fiber cone are also satisfies the S1 property. Well, let me. During this talk, I wrote many. I wrote some articles, but I didn't give a better reference. So the first one, our main motivation, the article Coefficient Ideals from Shah. The second one, we got one application for this ideal inspiration. The third one, it's we got the Ratliff-Rush ideal with respect to the maximal M, and also the last one, the article from another article from Shah. Thank you very much for your attention.
Any question? Remark, please. Is it possible to characterize other sales conditions?
Other
Other conditions of sale?
Oh, S2. Okay. To be honest, I don't know. I worked. I have some other articles with coefficient ideals, and I never was able to connect to S2, S3, just S1. In other art, sorry.
Are these known for the usual associated graded ring? They satisfy SM.
Como, Daniel? Você entendeu?
Se pro graduado associado é sabido para S2, para S3.
No either. No. Just S1 also. Just S1.
Please go back to the slide where you stated.
Yes.
Mentioned the paper by Ulrich.
Oh, yes. Yes, it's German. Yes. Here, right? Yes. Okay.
So you're assuming that I is normal.
Yes.
That every power is complete.
Yes.
Closed. So if you replace this hypothesis to the condition that I is integrally closed for high powers, say from certain m on, then you can replace the bottom line 1 by m. I mean m greater than or equal to m.
If you can replace, entendeu?
Se você troca,
Fala em português.
Ah,
se você trocar toda a potência do ideal é integralmente fechada, você está assumindo isso.
certo.
Se você assume que a partir de um certo mzinho.
Para N suficientemente grande, né?
Então você vai trocar esse 1 de baixo por m.
Para N suficientemente grande também na consequência,
O
né?
mesmo m.
Uhum.
Você supõe que a partir de um certo mzinho, ele é integralmente fechado, o ideal. Então, no resultado aqui embaixo, essa igualdade vale para mzinho maior ou igual que o m.
I don't know, to be honest.
Translate this question.
Sorry. I'm sorry. He said. Okay. Please.
That I is normal. So I'm asking whether if he replaces this condition by assuming that I is integrally closed for high powers for n equals n, say on, alright? Then you can replace, then you have on the bottom line here that is holds for n at least or equal to n. Say n.
The lower MIN may not be MIN for lower powers. It may be true for high powers. For monomial ideals, it happens. The problem is the integral closeness for the smaller powers. If it happens up to the dimension for monomial ideals, it will happen beyond the dimension.
I see. Yeah, but on the other hand, the result will be weaker, of course.
Yeah.
It will go just for n from n.
Right.
Another question, just a second question.
Okay, go ahead.
The
Go ahead.
nice example you gave illustrating that the Fabicon may not satisfy S1.
Yes.
Would you put that slide?
Yes. Let's go there.
Yeah, example. This ideal I is actually multiple, right? It has a length spread 1 and height 1.
Okay.
Do you know whether, this has any influence on the result, on the fact you illustrated?
No. I knew that the 5-icon here, it's actually it has one dimension. I knew. I didn't want to. I didn't put this. I didn't write in order not to confuse with the results. Okay, but we can use this for higher dimension. It's not a problem. For this example, it happens in this example, but
You have examples?
yes.
But non-multiple ideals?
Yes.
Thank you. Okay.
Yes.
So, more questions, remarks? If not, let's thank Pedro again.
Thank you very much. Thank you.